Firstly, I would like to apologize to everyone. I was tested positive for COVID-19 on Saturday, and my symptoms are still severe now, which leads to my voice a little bit strange. So I'm so sorry. I cannot show my best form. Okay, welcome to my project presentation. My name is Zhili He, and my project name is Infrastructure Correct Segmentation, Boundary Guidance Method, and Benchmark Dataset. Instructor is the Professor Zhang, coming from CSE. My presentation today is divided into five parts: introduction, make a dataset, methodology, experiments, and the last one is the conclusion. Okay, first of all, let's move on to the first part, introduction. Firstly, we can look at these four images taken from the actual inspection project. For figure 1, it's the cable inspection, and the workers' working height is more than 100 meters, and they have high safety risk. Then it's underwater structure. It has large blind area, and then it's a high pier inspection. It is inefficiency. Last one is the bridge inspection. We don't have needed too many complicated devices. So in general, there are 5 sore points for current methods, namely too much inspection blind area, high labor cost, low inspection efficiency, high security risk, and the last one is uncertainty due to the subjectivity of engineers. On the other hand, for the current situation, the situation is the extensive infrastructure needs effective inspection and diagnosis. So there is a sharp contradiction between the current methods and the current situation, which leads to that there are too many collapse accidents due to negligence inspection and failure to repair. So we see that there are too many collapse accidents. For example, in Taiwan 2019, Wuxi 2019, Changsha 2022, and too many people died because of the buildings, the bridges collapsed. So there is an urgent need. A new generation of accurate, intelligent, and convenient security diagnosis technology. So I want to ask, what is the next generation inspection method? We all know that the rapid development of AI technology has brought disruptive solutions to various industries, such as the latest AI products, ChatGPT or GPT-4, developed by OpenAI. I think everyone all have already witnessed its magic. So the most promising and inevitable solution is introducing AI into infrastructure inspection to empower security diagnosis and solve bottleneck problem. Because among multiple structural damage, cracks are one of the main forms, and this is correct. And the characteristics of crack, such as the length, width, and density, are also important indicators of structural performance degradation. So this research focusing on intelligent crack inspection. Based on AI, we don't need complex manual measurement anymore, and just a neural network. It can achieve the end-to-end pixel-level crack segmentation. Okay then, let's move on to the second part, make a dataset. The performance of models is highly dependent on data as a data-driven technology. However, almost all the images in the notable datasets are asphalt pavement cracks, such as Deep Crack in 2019 and Crack 500 in 2020. However, steel structures are one of the most common forms in civil engineering. For example, this is a steel bridge and this is steel high-rising building. And they extremely prone to fatigue cracks during surveys. And these images are taken from the real steel crack structures. And so we know that we need a high quality steel crack dataset. To do that, I make a dataset. Firstly, I prepare images with cracks, and they all have 4K resolutions. And then I make pixel level manual labels. I have to say it is a time killer. I spent most of time this semester doing this work. And then it's the same. There are some simple data augmentation strategies. And firstly, I retooled these images for 90 degrees, 180 degrees, and 270 degrees, and then I flip images vertically. And last, I rotated the images again. And step 4, I crop small pages from images and labels. And crop size is 512 times 512. And last one, I shuffle the data sets. And I take the top 303 3,300 images to be the training set, and take the remaining 525 images to be the validation set. And I repeat step 1 to step 5 to get the test set, including 530 images. I think about in next month I will publish this set on the GitHub website. Okay, let's move on to the part 3 methodology. Fourthly is the research form. We all know that the next generation inspection method is combining AI. So there are so many research papers related to crack identification using AI. I searched crack in one top journal called Automation in Construction, and its IF is more than 10 points, and it's a top journal in civil engineering. And we all know that in 2021 it has published 110 papers, and in 2022 it published more than 150 papers, and in 2023 it has published more than 40 papers. So there were too many papers related to crack identification using AI, and by researching these papers, we know that the core idea of these papers are they just use cutting-edge civil models to identify cracks, such as transformers, all kinds of attention modules, and all kinds of backgrounds. However, they neglect the intrinsic characteristics of cracks themselves. We all know that if we want to solve the problem truly, we must understand it. So, what is the intrinsic characteristic of cracks? I think the inherent characteristic is that the cracks can be decoupled into edge area and internal area. And as shown in this figure A, it can decouple into two parts. However, in these papers, almost no one has considered the edge of cracks. On the other hand, we know that in the human vision system, edge information is always adopted to help us distinguish, identify, and locate objects, as shown in figure B. If we want to identify the head of the panda, we will inevitably use the edge information, and I have draw a red line in the edge of the head of the panda. Yeah, we can fill this by ourselves. And if we want to locate the head of the panda, we will use this red line, namely the edge information. And on the other hand, in computer vision, edge information is helpful and useful. Some researchers have substantiated that integrating boundary features can improve models' perception accuracy and can generate more accurate segmentation images, such as SCI in 2019 and decoupled SegNets in 2020. So a question, can we integrate edge information into crack identification? With this question in mind, I have made some attempts, and I propose a model named Boundary Guidance Crack Segmentation Model, shortly BGCrack. And it includes 4 stages. Stage 1, backbone, and its function is to extract the features and extract the features. And step 2 is boundary feature modeling. Step 3 is global feature modeling, and the last one is stage 4. It is the feature joint optimization. And the data will be fed into step 2 and step 3 after passing through the step 1. I will introduce some core modules of this BGCrack in the next slides in detail. Fourthly, in the boundary feature modeling, and the core module is the high frequency information enhancement module, shortly HFIE. Let's see the motivation. In FCANet, researchers design a module. This is a module to capture high frequency information using DCT, discrete cosine transform. However, by researching this module, I find this module has two key drawbacks, and we can see that. The firstly, it draws into unreasonable prior information, that is, different channels correspond to different frequencies. We can see this image. For channel 0, the frequency is DCT 0. For channel 1, the frequency is DCT 1, and for channel n-1, and this is DCT n-1. So it's unreasonable prior information. And the second drawback is that it just considers channel-wise frequency and ignores the spatial-wise frequency, and it is the channel-wise. So in order to solve these two drawbacks, I propose the HFIE, and it includes two submodules. And the first one is spatial-wise, and the second one is the channel-wise frequency enhancement submodule. And then it's the global feature modeling. It's stage 3, and the core module is the global information perception module, shortly GIP. Let's see the motivation. We need the global feature perception. Why? And these two images can prove this motivation. As shown in figure A, it is difficult to judge which one is the real correct just based on this image, because there is the local information in this figure A. However, in figure B, we can easily know that the top one is the correct and the below one is the artificial marker, because in figure B, we have context semantic information and we have the long-term dependency relationship. And this is importance of the long-term dependencies. However, for CNN, its inherent characteristic is locality. So there is another contradiction. In order to solve this contradiction, I propose the GIP. And next slide, I will introduce the GIP. The GIP includes two branches. And the first branch is the DFT branch, namely discrete Fourier transform. And it can model the information from the frequency domain. On the other hand, the second branch is the transformer branch. I think everyone all knows the transformer because Professor Zhang have told us in the course. And owing to the self-attention mechanism in the transformer, and it can directly model the global information. So I embed the transformer into the second branch. And then I use 3 learnable parameters to fuse the features by the 2 branches. And this is the fuse formula. Okay, let's see the stage 4 feature joint optimization. And as shown in figure A and figure B, it is the self-feeding module and the cross-optimization module. For SFM, it is designed to promote information fusion of multi-level and multi-scale features. And for COM, it is further developed to promote the integration between the 2 kinds of features. And the first kind is edge features, and second kind is the body features. And the COM is developed to fuse the 2 kinds of features. And after features passing through these 2 modules, and they are fed into feature fusion modules, FFM. And FFME is for edge features, and FFB is for body features. And they are proposed to align the spatial dimensions, namely recover the size from this to h times w. Okay, that is the loss functions and the evaluation metrics. I use 2 kinds of loss functions, BCE loss and dice loss, and I use them to jointly train the model. And the BCE loss is a pixel level loss, and the dice loss is image level loss, and this is a total loss. And for the evaluation metrics, it also includes 2 kinds of metrics. First one is effective metrics, and that is the efficiency metrics. For the efficiency metrics, it also includes 2 kinds of indexes. First one is the number of parameters, and second one is the computational expensive. For the meaning of these metrics, you can refer my term project report. Thank you. Okay, let's move on to the 4th part, experiment. First one is the quantitative comparison. We can see the data in this figure, and we can know that our method has highest IOU, highest dice, and minimum parameter quantity, and minimum calculation quantity. And then is the qualitative visualization results. And based on this image, we can draw three conclusions. First one, it is the BG crack. This line, this column is the BG crack. The BG crack can identify different cracks accurately, no matter the backgrounds, features, and black and red artificial markers. And secondly, predictions are clear and have less noise. For example, in this image, and UNet and UNet Plus have too much noise. However, for BGCrack, it has a large noise. It shows our model has a stronger representation ability. And then, the predicted shape is more in line with ground truth. This shows the importance of integrating edge information. Our results are closer to the ground truth. Okay, then is the ablation experiments. It includes ablation studies of the boundary, feature modeling, effective validation of the gradient loss function, and effectiveness of the HFIE and the GIP. We all know that buying these ablation experiments and the effectiveness and the rationality of designs are verified. And then is the visualization analysis. And I use the GradCam I learned in this course to visualize the heat maps of feature maps. And we can see that BG crack focuses on the crack locations correctly. Okay, the last one, conclusion. Firstly, is the main contributions. Well, we know that we decouple cracks into two parts, boundary and internal area. And then we integrate the boundary information into semantic to generate more accurate and clear predictions. And then we also design some targeted modules such as HFIE, GIP, etc. And we use this module to enhance the reputation power of BG crack. And the last is the future work. Firstly, I try to improve the performance of inspection algorithms further, and then I want to combine some defect quantification tools. And then in the future, I want to build a civil GPT, and it integrates the planning, design, construction, and maintenance to assist civil engineers. And last but not least, I want to use the segment anything model, shortly SEM. I want to use this to help us reduce difficulty in labeling and increase data. Okay, that's all. Thank you for listening. If you have any questions, please feel free to let me know. Yeah, thank you. Bye bye.